Yeah, we'll work with it.
Any questions, problems you want to see, or maybe there was a stray implicit differentiation problem that you didn't like?
We should go over the homework.
Okay, so what do you want to see first? I budgeted 15 minutes for it.
Oh,
No, you can't see all of them.
It's only three.
24 problem, 3 or 4.
Yeah.
Okay, so give me the first one. Give me the first one. Huh?
Is it? We started with 3, right, y'all?
The 3 and 4.
5 squared, right? Yes. Equals 2x.
Just a minute, I'm sorry.
Okay.
Gotta remember I gotta do this because implicit differentiation. Okay, and what's the problem here? Tell me the whole problem.
5y squared
5y squared
equals 2x cubed minus 5y.
So right away I see these y ones are gonna have to be dealt with, right? So again, going from left to right, like I've been saying all along, right? So this is gonna be the power rule, gives us 10y, but we gotta do y prime. But y prime is equal to, y prime is equal to dy dx. Okay, that's equal to dy dx. So I'm just using shorthand here so I can move the variable around easier. That's equal to 6x, but I don't have to say x dot, do I? That's redundant. So obviously we're just gonna go to the y value here, right? It's minus 5, don't forget, y prime. You have to account for that y prime. So every time you take a derivative on a y one, you have to put the front y through the y prime times y prime. So if you follow the rules, then you have to add the y prime, which is why I cover the rules first, right? So now we got to solve this equation for a variable, something you've been doing for years probably, right? So there's a number of ways to proceed, but I feel like I want my y primes on the right side. So you can say 10y, y prime, plus 5y prime equals 6x. Now we should notice, oops, sorry, this fell over. You should notice, right, that there's a y prime in each term, which means we can factor.
Wait, why is it just 6x instead of 6x squared?
Yes. Should caught me there, right? Good job.
So even when it's written as dy over dx, you still know that you can take the y from that? What if it's not written as y prime, if it's dy dx?
You can do dy, it would just be 5 dy dx. I did make that stipulation here. So
Right, no, so I'm saying when you get to the, yeah, and if it's written as dy dx.
Yeah, you just go 10y dy dx plus 5 dy dx. Which nobody
still
does.
know to take the y from that, right?
Yes.
Okay.
But notice that as a consequence of the derivative of this being only minus 5, right? Then I just add the y prime. So I can take the derivative, then you add the y prime to it. All right, so over here we factor out the y prime. How's that? I get 10y plus 5 equals 6x squared. Does everybody understand that? Just factor out y prime here. It was common to both terms, so I factored it out. Why did I factor it out? Because I'm solving for y prime, right? I don't know if you remember when you cover the old literal equations, it reminds me of that from algebra. So you divide by this. And that leads us to that y prime is equal to what? 6x squared over 10y plus 5. This is perfectly acceptable. Now, I should stop today since I have time and point out to you that I could have said evaluated at the following ordered pair, right? I could have said evaluated at -2, 3, right? But it's obvious what you would have done, right? You plug in -2 for x and 3 for y, and you actually get a numerical answer. After all, this is derivative at a point, right? So at -2, 3, let's do that. Let's say y prime at 2, 3 would be equal to 6 times -2 squared. I didn't ask this originally. I'm just throwing this in to make sure you understand it right. Divided by 10 times 3 plus 5, or 24 over 35. Done. The answer is 24 over 35 if it's a -2, 3. Ready for the next one? Any questions on this one? It's a great problem for a test, for the final test. Obviously, I wouldn't do the exact problem, but you get the idea. I'm sure I'm going to ask you to evaluate some of these derivatives at a point, right? That's kind of like the whole point of the class. Ready to go to the next problem? This is number 3. I didn't number it. Let's look at number 4. Does everybody have it? All hearts and minds in agreement? I got a thumbs up over here, so proceeding. Got 2 thumbs ups. It's all over. That was really a good question that Bailey asked. You might have thought you didn't understand it, but I understood it perfectly, what she's asking. I'm with you.
The reason why I asked is because in my profession, we always use dy dx, never use y prime, so that's why I was just asking.
I knew that was what he had. I feel that when teachers use dy dx on this particular lesson, with all the movement of variables, it can confuse you. Because you're moving real quick, they're not explaining their steps, you know. I like the y prime, it's so easy to work with.
Yeah, it is.
Yeah. It's an old way, though. I could tell older teachers would use that. Of course, I'm not old, though.
She's an older teacher.
Oh, and she use dy dx, really?
Yes.
Give me her name, I want to look her up. All right, okay.
She's a good professor. She's a good professor.
You know, what you just said was very humble. I'd like to talk to you about that later. That's interesting you said that. What's number 4?
4x squared equals 2y cubed
2y cubed
plus 4y.
plus 4y. All right, that's a good one too. It's very similar to the last one. So this is 8x equals 6y squared y prime. Right? That time I remember about 2 there. Right, I remembered it. Plus 4y prime. If you do enough of these, you get the feeling, right? 8x is equal to, factor out the y prime like I did before, 6y squared plus 4. So usually on these things, the second to the last step is a factoring step, because you put all the y primes together. Usually that's going to be your step before the end. So you know you're at the end. Even on that big long problem I did yesterday, I got down to that step. Then 8x over 6y squared plus 4 equals y prime. Okay. I think you might learn calculus.
Maybe.
Make a little more sense?
A little. I mean, it makes sense like PEMDAS, but
Yes.
I don't know why we use this.
Yes, that's true. All right, anybody, do we need to go to the next one? There's one more I think I gave, right?
Yes.
The one that was long, right?
Yes.
Y'all can't wait for that one, can you? Now, you know what I'm gonna do this for fun? I'm gonna move on that problem at more of a moderate pace, like an instructor in college would. On the next problem, okay? Number 10, is it? Let's see it. Hit me with it.
x squared equals, parentheses, 4x squared y cubed plus 1 all raised to the second power.
Like that?
Mhm.
Oh, yeah. My kind of problem.
You don't need a
Bailey, stop it. Bailey, stop it. Just quickly curve the camera over and tell us. 2x, right, is equal to, here we go. I'm going to swing over here and reach back at it, okay? Is equal to 2 times this to the first power, but I'm not going to show it, right? So it's 4x squared y cubed plus 1. Now, it'd be cool if we could just walk away, wouldn't it be? But we can't walk away. We have to take the derivative of the inside, right? Which is why I think you guys want to see the problem. That derivative right there needs some attention. Okay? So, let's do it. 2x is equal to, in fact, you know what I want to do? I'm just going to take this and focus on this right here, okay? The derivative of the first times the second plus the first times the derivative of the second. 3y squared y prime. That's the derivative of the second. Plus 1 is just 0, right? So this is your derivative here. I can now simplify it. What do I get? 8xy cubed plus 12x squared y prime. That's what I'm going to put here, okay? Okay? Put a comma here because I'm just going to keep going. This is the equation here, really, isn't it? So I subtract 8xy cubed from both sides. Get 2x minus 8x cubed. You know what? I'm going to put it below there. Sorry about that. Put it below here. I get 2x minus 8x y cubed equals 12x squared y prime. Okay? Now all we have to do is divide both sides of the coefficient right here of y prime. And then I could say, I'm going to write the next line. I'm going to erase this. Okay, you guys saw that, right? I hope. I need the room below here. I didn't plan it well. So dividing out, we get 2x minus 8x y cubed divided by 12x squared y squared, and that's equal to y prime. And there's no real division. I mean, you could take out a 2 up here. Like, I'll go ahead and do that. Then make it 1/6 here, right? Or you just leave it like it is, and most teachers will accept it. But if you reduce the fraction, it would be 2x minus x. Oh, well, 2x. Look, this is it. It's 2x, actually. Excuse me, you guys. It's 2x taking out 1 minus 4y cubed all over 12x squared. It's worthwhile to do this. It is worthwhile, by the way. I think a teacher might expect you to do this because you can cancel the 2, you get 6 here. Cancel this, you get x here, right? And this is your final answer over here. It's 1 minus 4y cubed over 6xy squared. That's y prime. In this case, I think it would be worthwhile to factor out. Because you have a 2x you're going to factor out. This is common to both terms.
What happened to the 2 that was in front of the parentheses?
Let's see. This 2 here?
Yeah.
Yeah, it should be here still. I think, wait a minute, make sure. Let's see, I put this in here, I brought it over here. It's really here. It's here. Subtracted 8x squared from both sides. So it's there. So you think about it, I subtracted minus 8xy cubed here from both sides. That's why I dropped out. I didn't show it from both sides, that's all.
Oh, okay.
I was gonna do it at college speed. Because they just assume you know that.
Wait, say it again?
So right here, I just jumped from here to here just by subtracting 8xy. I didn't show it being subtracted over here, did I?
But where?
I didn't go minus 8xy, minus 8xy.
But where did the two?
2 is right here. It's right, let's see. It started out being here.
When did it become 2x, I guess I'm saying? Or, I guess.
There's 1 2x on the other side, and then,
Yeah, here the 2 came down here, right?
yeah.
So that became 2x over here. Or how did it? Oh, wait a minute. Oh, yeah, there is a 2. Wait a minute, make sure before I say that. Before I say what I'm going to say. Yeah, you're right. There is a 2 that should be here. You're right. 2 should be there. Which means that I should go back to here. Okay? I can't just put it down here. See why? I like that. I like these things.
I think there are 2 8x's.
So let me show you where it is. Okay. So 2x is equal to that I distributed. Oh, no, I didn't. Let's see here. It's 2x is equal to this. This is a derivative. You see this? You got to say 2x times the derivative of this. So what's the derivative of this? And that's why I erased here, remember? So let me write it down. It's derivative of the first times the second plus the first times the derivative of the second, which is 3y, y prime here, right? 3y, y prime. Then rewriting this, I said, we get 2x equals 8xy cubed, 8xy cubed, plus 8xy cubed, plus 12 x squared y prime.
Is that being multiplied by 2?
That's what I'm going to say. So that's where the 2 comes in, right here. So I would say you can divide both sides by 2. And you get x by itself is equal to 8x cubed, 8xy cubed, plus 12, 8x squared, y prime. Now you solve for y, right?
Wait, for that, the equation right there, the 3y y prime, wouldn't it be 3y squared y prime?
3y squared, y prime, 3y squared, y prime. So that means 3 times 4 is 12, x squared, y squared. There it is. So now you're going to solve for y prime. You're going to subtract this from both sides. You get x minus 8xy cubed equal to 12 x squared, y prime. Now I'm going to say you divide and you finish. There's no simplification. If you divide by this, right?
Okay, sorry, I didn't get that.
Yes. Let me finish first. So you get x minus 8xy cubed divided by 12 x squared, y squared. And I don't think there's any simpler you can get than this. There is no simplification there. Now I'll take a question.
Okay, because I was writing, so I lost it. What did you do with the 2 on the outside of
The two?
Yes.
Yeah, I kept it here. This is the 2 here.
Right, but when you continued on to
Divide both sides by 2. Divide both sides by 2, what happens? 2 cancels, you're left with x. So that's where the 2 goes. Okay, go ahead.
So in the beginning, when the 2
In the
was an
beginning,
x,
right here.
No, on the other side, the 2 was an exponent. So you just did the regular power rule.
Power rule right here, then the chain rule, right? You gotta do the derivative of the inside.
But when you do the chain rule, isn't it?
Derivative of the first.
But the derivative of the
Times-
first is multiplied by the first, I guess.
So derivative of 4x squared, what's that?
That's 8x.
Okay, and then times the second. Plus the first times the derivative of the second. That derivative is right. This is the 2 that I dropped out. The 2 that's right here. I put it back in over there. I divide both sides by 2, it's gone. So I only really took the derivative of this, right? Down here. Derivative of the first times the second plus the first term times the derivative of the second. That's called the product rule, right? Think about that. And then somebody said the 2's in front, so I put it there. But then I had 2x over here and a 2 here. So I divided out by 2 and I just got x. So that way down here, there was no cancellation I have to do. There was no cancellation. It's done. Now, if you have x and y as variables, you can put them in here. And this is not terribly clear, but 12 x squared, y squared. There you go. Okay. Not quite as long as I thought it would be. Because that other one the other day in class was longer. Okay. I can give you a couple more implicit differentiation problems that you can do. Write these down. How about doing one right now? Real quick. How about this one? No numbering, sorry.
How would you, I don't know if this is a question that you could really answer, but how would you know that you could have divided by 2? So when you have.
Because there's a 2 on both sides of the equation. I just divided.
Even if those multiplying by something else.
Yeah. I mean, basically, if you have 2 times something equals 2 times something, you can just do this. You divide both sides by 2. And you get square equals triangle. That's what I did here. Except the square was just an x, right? The triangle is just an x. How about differentiating this? I'll give you 6 minutes to try that problem. Solve for y prime, right? Oh, let's make this interesting. Solve for y prime. Get this, guys. Y prime at 0, comma, minus 3. Did you know that? Solve for y prime at 0, comma, minus 3. See what happens. I don't know what that's going to do. We'll see. First, you got to take the derivative and solve for y prime, right? Get y prime as a function of x and y. So it grades. I wonder if he's coming in. Another good problem. Then you can do this one over here. And this one here you can do. Well, let's do this one first, though. Like you guys do. Good solid practice. Okay. 3 minutes. Such neatness. Such neatness. Wow, look at that. How neat this is. Cats are really neat. I'm going to plug out the walls. Oh boy. Here we go. Maybe a minute and a half or so, and just follow along with me. It's like I may just do problems for the rest. Problems for the rest of this period, but we'll see. All right. Did anybody get an answer at least? No? Think you have an answer? Close? Sort of close? Meh. You want to take a shot at telling me? Well, I'll go to the end and you tell me if you did. So over here, it's just 2y, right? It's just 2y times what, Jordan?
2y times 2y or 2y equals
2y times
y prime.
asking me or telling me. Okay. Don't forget the y prime. Then that equals what, Mariah?
2x plus 3y prime.
Right. That's correct. So once you get here, it's just a question of manipulation, isn't it? How might we manipulate this, Jordan?
You can subtract the 3y prime from this.
What does it give us over here?
It would give you y prime times 2y minus 3.
Well, do the whole thing. You give us this first. 2y, y prime, minus what?
Minus 3 y prime.
Right. That equals 2x. Now what should we do?
Then you factor it out.
Factor what out?
Y prime.
And what's it going to look like?
Y prime times 2y minus 3.
Now what, Bailey? What's y prime equal to? Look at the board here, probably is better. What should we divide both sides by?
2y minus 3.
That's it. Just simple as that. It's done. Problem done. Now you got to plug in what? When you do that, the answer is y prime is 0. So there's no change at that point, which means that at that point the tangent is straight across. It means like it's probably like this. It's this point down here. That's where we just happen to take the derivative at it. Just coincidence. All right. Let's look at this beautiful one here. Give me guidance here. Jordana?
First you put 8 times x squared plus y 7 equals 0. Oh, right.
Don't forget.
Right, times 2x plus y prime.
Now what? Oh boy. Maybe this is one of those ones where let me just think for a minute. Is there a trick? Because really you can't because of the squat of the 7th, right? I mean, you could. Actually, you can. Oh, that's interesting. We have 0 here. So what do we do? Well,
I just divided the 8.
you divide what by what? What do you divide this side by?
8x squared.
Right? Divide by that on both sides. Do I have to do this side? Do I have to? I don't have to do it because that's going to be 0, isn't it? So what are we left with? This cancels. What are we left with?
2y plus 1
Equals what? Are you asking me or telling me? Okay. Now solve for y prime again. What does y prime equal? That's it. You only needed the y value on that one. You didn't need an x value to find the derivative. Sometimes people get stuck here, but you remember you're trying to get y prime by itself. That's all you got to remember. Whatever obstacles you have to overcome, overcome them. Here's one for
I
you.
messed up with the first part. It's 2x, negative 2x.
What's that?
I think you accidentally put aside it 2y plus y prime
Oh.
plus 2x.
I just did whatever you told me, huh? It's 2x. Good. So it's now it is dependent on x at the end. So what is the final answer?
Negative 2x.
Yeah, so it's only dependent on x. The derivative is only dependent on x.
Can we do more problems for the sheet?
We could, or I'm going to do one more of my favorite ones here. You should look at my favorite ones. See the hint? Here's one I like. How about this one? This is an answer that's going to have a trait function in the answer, right? So what's the derivative of the cosine? Excuse me?
Negative sign.
Minus the sine. Probably good to mention to you, this is not distributing sine. This is the angle here, right? This is actually the angle, if you will. But then we got to do something else, don't we? Do we not? Do we not have to do something? Well, the something is 2x plus 2y, y prime. Make sure I give room. Remember 2x plus 2y, y prime? These are the kind of problems that I remember I hated when I did calculus, but I got to show it to you. So, oh, good, I have colored markers, so that'll be helpful for you. So what I got to do here to solve for y prime is to take this and distribute it here and here. I've got to distribute it because I got to try to get to that y prime, right? Hopefully with the 0 here, it'll become easy for me. Hopefully. Which is why teachers do that. So we distribute this term. The first we get minus sine x squared plus y squared times 2x. And over here we get minus 2y y prime times minus sine x squared plus y squared equals 0. So now, almost there. So now, I'm going to get to change colors to show you what I'm doing. This is so good. I never had this in my day. Just had chalk. That's why we didn't learn it fast enough. Does everybody understand this step? I distributed this big expression to each term. Should I put it in front, but that's okay. In fact, that's what I'm going to do. I'm going to make this plus here. See the minus and the minus, you guys? Minus sine plus 2y, y prime, sine x squared plus y squared equals 0. Okay, so what I would do now if I were doing this problem is I would factor, well, no, I wouldn't. I would add this term right. One could add this term to both sides, right? Bring it over here. So I'm trying to get the y prime so I can divide out. And the signs are just going to cancel, which makes this problem a great problem.
David,
Yes.
how did the 2y prime become negative in the first? Because wasn't it positive in the first equation?
So when I distributed this, what do I get?
A negative 2y.
Negative 2y. But how did I get that? Oh, negative signs. This is all right. It's okay. Because we had minus sign we were distributing here. What's the minus times a positive?
Negative.
Boom. Now, we distributed a negative sign, so I can't get rid of it, can I? No. I did here, though, didn't I? Because a minus times a minus is a plus. I didn't want to do two things at once. So the answer is I went negative first, but I was distributing a negative sign. So there you go. So minus that. Is that right? Minus that. Minus times this is minus. So actually it's just minus this. So I think you're right for the wrong reason. So you're right. Let me show you. Signs here. No pun intended, signs, S-I-G-N. So minus times a plus is a minus. So we've taken care of the minus sign already. So correct your notes to look that way, and this is minus. So that is correct. I could have just continued from there. Now there's a number of ways to proceed because look at this sign x squared plus y squared. They're the same, aren't they? So one could say we could factor it out, but I don't think that gets us closer right away. What gets us closer is if I can add this to both sides. Just add that to both sides, right? What do we get? We get that dropping out because you added it. But over here you get, I better put it down here. You get what? What's left over here? 2y, y prime, sine of x squared plus y squared. Sine of x squared plus y squared. Divided by, equals, right? Equals sine of x squared plus y squared to 2x. Trying to solve for y prime, right? So in order to solve for y prime, the things that are underlined have to be divided by both sides. This has to be divided out to leave this by itself. Now it'll be all by itself, right? Now we go over here. We get y prime is equal to, now when you divide out by everything, let me show it. We get this sine of x squared plus y squared times 2x divided by 2y. Put 2y here, okay. 2y sine of x squared plus y squared. Okay, that's the problem I was hoping for. Well, I think you can see that if you divide by that, you got a lot of cancellations here. Y prime is equal to, this cancels with this. They're exactly the same, you see it? By the way, you learn later those are really one. Sine of x squared plus y squared is really one, but don't worry about that. That's a trig function, but it doesn't matter, they cancel. over 2x over 2y, which gives us y prime is equal to x over y. So all that to get x over 1, I think.
So this is that what I'm looking on the test?
This is not a good test problem. It's a good one for exercises, though.
I think he took away the negative from the 2y prime.
So let's see. When I divide it both,
So that it was a negative, right? Or no?
well, add it to both sides.
No, the negative 2y prime.
Wait. You mean here?
No, other side.
Here?
These two instead.
The negative 2y prime, that's right before the parentheses.
Right here?
Yes, that one is.
Okay, so we're there. Where were we here? So right here, yes, right? Guess we're probably divided, well, when we divide both sides, right here is where we lost it. So we divide it by minus 2y. So now, I think it's down here, right? Well, either one, right? You can go to either the top or bottom, so it's there. Just off by negative. You can either go x over minus y, minus x over minus y, or minus x over y. All of them are the same. So this would be a good practice problem to see if you get the same answer. You're going to find out a lot when you do implicit differentiation. When you check the answer in the back after a long problem, you'll see little things like that. Because, you know, the manipulations at the end are actually more challenging than the actual derivative, which is why I always save implicit to last. It should be saved to last. The technique isn't so bad. You saw the one we did before that was easier. Let's pick a harder problem this time. The good ones for the test is the one I did right before this one. That was a good one. That's a good one. All right. What time? Time check, timekeeper? Okay, good. All right. Let's suppose we have a ladder laying next to a building. Oh, before we do that, let's give you some significance of the derivative first. So, no, you guys are ready. So here's a wall here. Here's the ground here. There's a ground, there's a wall. Okay. And let's say the wall has a length of L, L1. Down here, the ground, there's a ladder that's laying. I was doing a preview of this earlier. Say we have a ladder that's laying against the building, like this. I'm a bad artist, but you get it. There's a ladder laying against this building. This length here is L2, from here to here, okay? And you're sitting there watching it, right? You realize that the ladder slips loose here and begins to slide down the wall, right? Making this triangle, right? This right triangle changes, doesn't it? It begins to go here, and here, right? It slides down, thereby making this ground length change. So the ground length is changing as the wall length goes down. So what you have here is the right triangle with this equal to L1, this equal to L2. I'm going to call this just C here, right? As the ladder slips, I'm going to say it twice, 3 times actually. As the ladder slips, L2 gets smaller at a certain rate of speed, doesn't it? And L1, eventually it'll be 0, but it doesn't stop slipping, doesn't it? It'll slide all the way down. And you watch it slipping. Let's write an equation to define the motion of the motion of the ladder on the 2 sides. In other words, how the right triangle is changing over time. It's changing because it's going to go from looking like this looking like this, looking like this, looking like this, until it falls all the way down, right? So the ground is getting longer and longer. L2 is becoming bigger and bigger. So we can see it's becoming bigger and bigger. If we could take a picture, we could use the Pythagorean Theorem to figure out what each side is, couldn't we? We could do that. In fact, what does that look like? C equals L1 squared, C squared equals L1 squared plus L2 squared. Somewhere before you saw that in your life, right? It's called by most of you the Pythagorean Theorem. Of course, I call it the Cometan Theorem. Bet you don't know why. The Cometan Theorem. That's the name of ancient Egypt. And that's where they first discovered this theorem. Yes?
You said before there was the Pythagorean theorem, but if we're doing like directional, since one's going down and one's getting smaller and one's getting larger, wouldn't it be a negative?
No. Because in general, you're squaring a negative. Lengths are never negative. Lengths are always going to be a certain scalar. So it's getting a smaller and smaller number, is what we'd say. Now, what I thought you were going to say was, and you didn't exactly say it, was that what I think you were saying, that the rate of falling might be increasing, the other one decreasing. I don't know. It depends on the numbers involved, right? Which one's slipping faster is another whole thing. So we can write an equation to discuss this motion if we take what's called a time derivative. A derivative of each one of these variables with respect to time will reveal to us what the equation of the motion of the latter is in the, I'm going to say, in the horizontal and the vertical and horizontal direction. So dc dt. Now notice I bring in a third variable because it's time. I could have differentiated with respect to each side, but in science it doesn't really. We're interested in the rate that it's falling down the wall too, not just where it is on the wall. It's the rate too we're interested in. This is moving. This system's moving fast. Equals dl1 dt plus dl2. Oh, I'm sorry. I forgot I had a power rule here. Excuse me. It's 2L1 dl1 dt. See the power rule? You see it? Plus 2 dl2 dt. Okay? Here comes the question. Oh, we hate using dc dt, dl dt. We don't do that. We bring in not the prime, but the dot. The dot means a time derivative. Everybody say it. Say the dot means. Everybody, the dot means a time derivative. Because we're going to look at rates. Rates mean distance over time. Okay. So we could say C dot is equal to 2L1 L1 dot plus 2 L2 dot. I don't like the way these came out. So notice the dots on each one meaning DL dt, DL1 dt, DL2 dt, and DC dt. So what does your instinct tell you about the C? Is the C, the question is, since these two sides are the ones slipping, they're slipping, right? I don't know. Does the length of C change? Does the lateral length change? Really? Does the lateral length actually change, or does just the sides change? Is that a no? No, it doesn't change. The ladder stays the same. So, yes.
Is that what is that? Is that a comma or?
Here, there's 2 here. 2L1.
Oh, it's 201.
L1 dot. Okay. The point is this C dot is 0 because the ladder length doesn't change. The ladder length stays the same. It's a constant. We could have just put a number here. C squared is just going to stay the same. It's not changing. There are problems with it. They can make it change, but it's not changing here. So what do we get? We get that 0 equals 2L1, L1 dot, plus 2L2, L2 dot. Oops, dot. We say that this equation here is the equation based on the time derivatives or a related rate equation because there's rates that we can relate to each other. Now I must note that if we knew how fast the ladder was slipping here, we know the lengths of the sides, don't we? We can figure out how fast it's slipping. So I'm gonna write a word problem with this exact system right now and relate each term to each term. So the way these problems usually develop is a ladder. I think I have one in the homework like this. A ladder is laying against, probably lying, I don't know. It's laying against.
Do you want the exact wording?
Yes.
It's an 8-foot ladder, it's leaning against the wall.
Oh, we can do that. Good. I didn't know you guys had it. An 8-foot ladder
It's leaning against the wall.
is leaning against the wall.
The top of the ladder.
Hold on.
Oh, sorry.
Against the wall or a wall, whatever.
The wall. Against a wall, I'm sorry.
A wall. Okay.
The top of the ladder is sliding down. At the rate of 2 feet per second. How fast is the bottom of the ladder moving?
How fast? Okay.
Along the ground at a point.
At a point.
Oh, I'm sorry, at the point in time.
The point in time.
When the bottom of the ladder is 4 feet from the wall.
I'm moving a minute here. I want to refer to while I'm solving the problem. That's why I wrote it out. So you guys can see how to do it.
Ben, what was that?
Excuse me?
This is the worksheet.
It's on the worksheet. Related rates. I gave it to you yesterday.
July 13th, if you look in your email.
But I wrote it down
It's
here.
number 1.
Yes.
It's number 1, yes. Oh, she wanted a number, yeah. That's pretty good. So you just look at it. It's here too. So I can draw a diagram with this, right? The diagram looks like this. It's an 8-foot ladder. I'm gonna draw it like this, okay? This distance here is 8, but it's a constant distance. Okay, guys, it never changes. The 8 feet's never gonna change. What changes is the sides of the triangle. I'm assuming it's a right angle. It's at the wall and the ground, right? The top of the ladder is sliding down at a rate. So I'm gonna say right here, I'm gonna call, now this might make it a little easier, right? I'm gonna say A and B. How's that? Okay. So I'm gonna call this side B and side A. As a, you know what, do we say lengths? We say lengths too. So I'm leaving AB, and I'm gonna say that, I'm gonna do segments, okay? Okay? So this, when you say it's sliding down, this is a line segment AC, right? That's AC, right? You guys see that segment AC? So segment AC is changing at a certain rate, right? So really, this is AC dot. This length, this velocity here is AC dot. So I'm just going to say d AC dt. That's what this velocity or rate. Because what does it say? It says the top of the ladder is sliding down at a rate of this, 2 feet per second. Okay? So every second, 2 feet down the wall. It's not long before it falls, huh? How fast is the bottom of the ladder? This is where, I see what you were saying a minute ago. We'll get to in a minute. How fast is the bottom of the ladder moving this direction, right? Which is dBc dt, right? Segment BC. How fast is that changing? How fast is that changing? At the point in time when the bottom of the ladder is 4 feet. So that's when this is 4 feet. So we know this is 8 feet, that's 4 feet. Okay. Almost there. So the first thing you do in any of these problems is take the derivative. You take the derivative. So you can see I said this was length A, this is length B. If you want, I can call this length C. So we get an equation. C squared equals A squared plus B squared. Okay. But you remember you got these rates we're going to put in a minute once we take the derivative. So let's take the derivative. We get 2C dC, or to say C dot. This is 2A, A dot, plus 2B, B dot. Remember, this right here is really B dot, right? According to this diagram here. And this here is really A dot. Okay, since one is increased, well, wait a minute. Let's see what we know and don't know. I always say when you take that derivative, let's see what we know and we don't know. We do know C, but what's C dot? What's the time derivative of 8? Well, the answer is 0, because we said the ladder length does not change. It stays the same. And that happens in every related rate problem. You have to identify what stays the same, given the diagram. So here, that's going to be 0. How about A? Do we know A? I think we do. I think it said it was 4 feet at the time we're investigating. So this is 4. Do we know A dot? Well, that's what we're trying to find, I think. They want to know, what did it say? How fast is the bottom of the ladder moving on the ground when it's over? Okay, it's 4 feet from the wall. Okay. So this is 4 feet from the wall. The only thing we don't know when we look over here, do we know what A dot is? That's the thing we're trying to find. That's the mystery, right? But then look at this one. Do we know what B is? B dot. Do we know what B dot is? We know how fast it's slipping down the wall. Not related rates. You just have to read the problem 3 times. How fast is it slipping down the wall? 2 feet per second, and that's where your negative comes in, right? So it's 2 times minus 2 feet per second. Not that, minus 2 feet per second, because it said the rate was feet per second. Whenever you see something per something, it's a rate. If it's time, it's per time, like per second, per minute, per hour. It's a derivative. Now, do we know what B is? Do we have any guys? This is 2B. That's not. Do we know what B is? Can we find B? Any suggestions? Can we find? Because we can find B. This problem's over, isn't it? We can get A dot. But I know how to find B. We know the ladder is 8 feet, right? Yes?
Would you use the regular Pythagorean?
Yes, you would. So you can find B. So there's two parts of related rate problems. There's a derivative and identifying what variables you don't know. And almost always, the way the problem is written gives you a hint at what other equation you can use. In this case, it's A squared equals B squared. 8 squared equals 4 squared plus B squared. Where 64 minus 16 equals B squared. Or 48 equals B squared. And what do you get here? You got 24, 16 times 3, right? So the square root of 16, so 4 radical 3 is equal to B. That's what we'll go here. So we know everything except A dot. We can solve for A dot. Let's see what we get. Okay. So we have over here 0 equals 8 times A dot plus 2, not plus, minus 4 times 4 radical 3, or minus 8 A dot, almost there, is equal to minus 16 radical 3. If we divide both sides by negative 8, and we get that A dot is equal to 2 radical 3. Well, somebody might say 2 radical 3 what? Feet per second, because that's what we've been using. Again, A dot, to look at the original problem, is how fast the wall is slipping away. Notice it's positive, that makes sense. It's getting bigger. It's going in this direction anyway. So this 4 is going to get bigger and bigger from that moment on. Because at that very moment, this is a snapshot, right? It's going to get bigger and bigger and bigger until it lays down flat. By the way, the maximum it can be is 8. Because when this ladder lays down, it'll be 8, right? But it's moving toward 8 at a certain rate. What rate is it moving toward 8? 2 square root of 3 feet per second. That's a lot. So in about 3 seconds, it'll be flat. It'll fall to the ground. Now tomorrow, I think we're almost to the end now, right? We should be at the end. I don't have time to really slowly develop this. But what you're going to see is that we're going to do a sphere problem after I do 2 more of these. You're going to see what's happening here is that we started off by just taking the derivative, right? A time derivative, though. The derivative with respect to time. And then we ended up using something about this setup, using the original equation to figure out what we're missing. The key step is here to figure out what are we actually missing. What do we know, what we don't know. Tomorrow I'll take you through that much slower with the same problem. Then I have 2 other problems in the assignment like that. So related rates won't be on your final, whatchamacallit, but it is something you might want to put in your notes. So I think by the time you get to related rates, you guys will already be experts. It'll make more sense. But I'm going to cover it again tomorrow. Put it in your notes. But the other stuff we've covered up to this point, including implicit differentiation, will be on that final sheet. it's fair to put implicit derivatives on there. Will I have a big long one? No. Probably have one or two that are going to be straightforward. I told you the ones I liked. I covered you. You're going to have, chain rule, product rule, trigonometric functions, sine, cosine. And one problem where you have to put it all together, you have to synthesize. I'm going to give you a chart of derivatives and say, what's this derivative here? Okay, not bad at all. I told you I always end up like a exciting cliffhanger.